Welcome to Ask and Learn.
In this problem, we have basically a barrier here, a bulkhead that runs up from the ground, and then there's water over here that is 4 meters deep, and then there's soil over on this side, which is 6.5 meters deep over to the base of the bulkhead. And then we also have an embedded rod in here that is kind of fixed to something fixed over here, like some rock or something, to help support this from kind of collapsing over. Obviously, if this were a beam, it would have some bending strength to it, so it might not need this. But actually, what happens if you're a civil engineer or want to be a civil engineer, one of the things you have to worry about is that the soil gets wet, and the wet soil is a whole lot heavier than dry soil. So all of a sudden, if you design this and everything, and you design it so that you have, what the soil density is and the weight, so that it holds that, but then it rains, and then the water absorbs into the soil, and now all of a sudden you have a whole lot bigger load than you anticipated over here. So if you actually look at most bulkheads, especially just retaining walls, you'll see that they actually have kind of holes in them to let the water on this side drip out, so that we don't have we don't build up a lake on the other side, on a lake in the soil. Anyway, that's a little side bit. So we have F1 here, the action force at the ground. I guess we'd also maybe think about putting a reaction moment here, but then we'd have too many unknowns. And basically, this is trying to provide that moment, because really we don't really want a lot of moment. This beam would be carrying a great deal of moments, so that it doesn't bend or break. I'm calling this the origin. F2 is our force in the what do you call it? What did we call that thing here? Ground anchor. Yes, the ground anchor. And it is 6 meters up from the base here. The load from the soil, and we're told that this is now, this gets up to 310 kilonewtons per meter. So basically, given some density of the soil, we know what that is. And again, if that's wet, then this might be a whole lot larger. But maybe, hopefully, they're designing it so that when it is wet, that's what you get. So the equivalent reaction force, the equivalent load here, is the area under this curve, which is 1/2 6.5 meters times 310 kilonewtons per meter. And obviously it's in the negative horizontal direction, and it's in kilonewtons. And then the distance is 1/3 up from the base here, so 1/3 the way up. So 1/3 of this length here, and that's 6.5 meters. And then we have the reaction force over here from the water, and down here we have a maximum, the maximum distributed load is, let's see here, 118 kilonewtons per meter. And so this is 4 meters, so the magnitude is 2 times 118 in kilonewtons. And then it is now 1/3 of this length up from the base, so it's 4/3 of a meter up here. Then we also are asked to include the weight of the bulkhead itself, which just adds another force in here. And it acts, the centroid is somewhere up. I guess we could assume it's in the middle here, but it doesn't really matter where, if this thing were non-uniform, where it is, because this force is, the moment is just going to go through the origin here, so it's not going to create a moment. So in this problem, we have 5 forces and 5 position vectors, but still we can sum them all up, get our forces and moments. But we still only have 3 unknowns, this, and this. So we'll get 3 equations and 3 unknowns. And if we plug in all our numbers, we'll get that F1x is 460 kilonewtons. F1y is minus 7.85 meganewtons. So a lot of, that's pretty much the weight. In fact, that is the weight of the bulkhead, which obviously we'd be concerned about making sure that it doesn't sink into the soil down here. And then F2x is 311 kilonewtons. So we have it's obviously pulling the wall back, keeping it from folding over from the weight of the soil.